These are an ongoing series of extraordinary airplanes existing at the extreme cutting edge of technology. The X-planes are radical, often bizarre, machines that push the boundaries of what is possible to an astonishing degree, sometimes at the cost of test pilots' lives. We have chosen a diverse bunch of these exciting airplanes, some excellent and some terrible, to illustrate the incredible achievements of these remarkable machines. The order and selection are somewhat arbitrary, but we had to start somewhere. These are the top 10 extraordinary experimental airplanes in the world. Number 10, Boeing X32. If any other experimental airplanes have become a popular meme, but the X32's air intake's resemblance to a cheerful grin has earned the Boeing X32 a surprise cult appeal that far outlives its flying career of 2000 to 2001. The X32 was built as a concept demonstrator airplane for the program that eventually led to today's Lockheed Martin F-35 Lightning II. One of the hardest tasks the X-32B variant had to attempt was vertical takeoff and landing. Whereas the rival X-35 used vectored thrust and a lift fan, the X-32 came with a different solution. The main exhaust vectored thrust was combined with two lift nozzles in the fuselage. The X-32 proved a troubled design. The basic configuration was different to what a notional F-32 would be, which did not impress the Department of Defense. The airplane was also overweight and underpowered, and vertical takeoff required the prior removal of a section of the airplane. The rival Lockheed Martin X35 was selected, leading to the F-35 Lightning II in service today. Though unsuccessful, the Boeing X32 was a charismatic and intriguing design that offered a very different approach to the creation of a supersonic, stealthy fighter bomber with a short takeoff vertical landing, STOVL. Number 9. Grumman X29. Today, almost every airplane that travels faster than 500 miles per hour has a swept back or delta wing. However, this isn't the only solution to high-speed flight. The swept forward wing offers several advantages for the same given wing area. Among them, a higher lift-to-drag ratio, better agility, higher range at subsonic speed, improved stability at high angles of attack, and a shorter takeoff and landing distance. In 1977, thanks to the advent of stronger materials, the U.S. Defense Advanced Research Projects Agency, DARPA, returned to this promising idea, and along with the U.S. Air Force Flight Dynamics Laboratory, now the Air Force Research Laboratory, issued proposals for a research airplane designed to explore the forward-swept wing concept. To save time and money, the Grumman Company proposed an X29, which upcycled many parts from other existing airplanes, and it defeated a rival bid from General Dynamics with a modified F-16. The two X-29 airplanes were flown at NASA Ames Dryden Flight Research Facility, now Armstrong Flight Research Center, at Edwards Air Force Base, California, from 1984 to 1992. The forward-swept wings were mounted well back, with canards, horizontal stabilizers to control pitch in front of the wings. The X-29 demonstrated dazzling maneuverability, supersonic performance, and an impressively light structure. Air moving over the forward-swept flows inward toward the root of the wing instead of outward, as on a conventional airplane. This reverse airflow kept the wingtips and their ailerons from stalling at high angles. Number 8. Conair X6. It is a mind-blowing fact that America made great efforts to create a nuclear-powered airplane, strategic bomber between 1946 to 1961, spending the equivalent of well over $10 billion doing it, and some estimates are much higher still. Without reliance on liquid jet fuel, it was hoped such airplanes could fly for weeks on end, providing a constant state of readiness and limitless range to hit any target. The Conair X6 was a proposed X-plane converted from the NB-36H to mature the nuclear-powered bomber technology. The Conair NB-36H was an experimental airplane that carried a nuclear reactor but did not use it to power the engines. Instead, it was there to test the safety of its shielding and airborne operation. The extremely alarming NB-36H flew for a total of 215 hours over 47 missions, during 89 of which the reactor was operational. The experiments took place between September the 17th, 1955, and March 1957 over New Mexico and Texas. In 1961, President Kennedy canceled the entire program, citing the immaturity of the technology and great costs involved. And in any case, nuclear ICBMs fulfilled most of this plane's intended purpose. The Conair X6 itself was never to fly, which many people, considering the catastrophic risks in a potential accident, may consider a good thing. Number 7. Ryan X13. Vertige 1 approach to vertical takeoff and landing was the tail sitter. This is an airplane that takes off and often lands with its nose in the air and tail on the ground. It is a tricky technology requiring an awkward and potentially deadly transition from horizontal to vertical flight. Another difficulty for a tail sitter is the position and view of the pilot. The Delta triangular winged airplane used a British Rolls-Royce Avon RA .28 turbojet. Pitch and yaw control in the hover was achieved by vectored engine thrust, whereas roll control was provided by small puffer jets. The airplane first flew on December 10, 1955, and during testing achieved a rather modest top speed of 350 miles per hour. The X-13 was more successful than its turboprop tail-sitting brethren, but was championing the wrong approach. In an attempt to promote the airplane, Ryan arranged for the X-13 to cross the Potomac River and land at the Pentagon. The thrust-to-weight ratio of 1.48 was extremely impressive and one of the most dramatic in history. To put this into context, today's powerful F-22 Raptor fighter has a maximum thrust-to-weight ratio of around 1.25. Number 6. Bell X-22. One way to achieve vertical takeoff and landing is to direct the thrust by swiveling your entire engine. Airplanes with propellers mounted in wingtip swiveling ducts have been a staple of science fiction for some time. But they are even older in reality, dating back at least as far back as the X-22 of 1966. The three-bladed propellers of the X-22 were mounted on 4 wings. The propellers were driven by 4 gas turbines mounted in pairs on the rear wings. Control was achieved by tilting the propeller blades and the use of control surfaces, elevators and ailerons, which were located downstream of the propellers. The Bell X-22 was created to explore the plausibility of a fast VTOL troop transport and controllability issues of wingtip swiveling ducts. It first flew on 17 March 1966. It achieved a top speed of 310 miles per hour, 515 kilometers per hour, which is far faster than a conventional helicopter, but slightly shy of the target speed of 326 miles per hour, 525 kilometers per hour. Today, the militaries of the US and Japan operate the Bell Boeing X-22 Osprey. The Osprey is not a tilt-wing design, but a tilt-rotor design in which only the engine moves. There were several reasons why the tilt-rotor has been more successful than the tilt-wing one, being the sail effect of the tilted wing during takeoff and landing is very hard to control. Number 5. Douglas X3 Stiletto. On looks alone, the extraordinary sleek Douglas X3 appears to be the fastest airplane ever made. Its elongated, needle-like nose and minute wing suggest an astonishing swiftness. Indeed, it was built to be one of the fastest airplanes in the world, studying prolonged flight at Mach 2+. Looks, however, can be deceptive, and the X3 was able to achieve less than half its intended top speed. Rather than Mach 2+, it failed to even reach Mach 1 in level flight, largely due to it being chronically underpowered. Unlike the earlier Bell X1 and X2, the X3 was to use jet engines, but this would cause problems. Engine developmental issues resulted in the X3 having 18% less power than required. The original planned engine type, the Westinghouse J46, grew too large in diameter across its development and was replaced with a smaller weak engine type, the Westinghouse XJ34WE17. Though it failed in its goals, the X3 did at least pioneer the use of titanium in major airplane structures, and less laudably, the achievement of one of the fastest takeoff speeds of 260 miles per hour. A useful spin-off of this high-speed takeoff was that it inspired a new generation of tires of greater heat resistance. Number 4. Hiller X18 Propelloplane. Eliminating the need for a runway gives an airplane an enormous degree of flexibility, allowing operations wherever required. While a helicopter can take off and land vertically, it is far slower than an airplane. The search for a faster form of vertical takeoff and landing, VTOL, has been approached in many different ways. One way to affect vertical flight is to rotate the entire wing, including its engines, 45 degrees, a concept known as a tilt wing. To save money, many parts were scrounged from other airplanes and projects. Its massive coupled turbofan engines were taken from a canceled VTOL fighter project. Control and pitch came from a Westinghouse J-34 jet engine. The X-18 first flew 24 November 1959, and 2 issues with the concept were soon abundantly clear. A large vertical wing acts like a boat sail, affecting controllability in the landing and takeoff cycle. And if one set of coupled engines were to fail, the result would be disastrous. The solution to the latter problem would be cross-linking both sets of engines to both propellers, a complex solution used today, the V-22 Osprey. The X-14 was not the first attempt at a tilting, with the German Wasserflug P-1003 concept predating the airplane by some 21 years. The X-14 would also not be the last. The tilt wing concept returned in the 2018 Airbus A3 Vahana, a technology demonstrator for semi-automated flying cars. Number 3. North American X15. The U.S. series of ever-faster crewed X-planes reached its zenith with the spectacular North American X15, an unparalleled airplane that remains the fastest human-crewed airplane ever made, despite the record being made in 1967. Carried to height nestled beneath the wing of its NB-52 mothership, it was released at 45,000 feet altitude at a speed of around 500 miles per hour. It was then that its rocket propulsion would push the airplane to speeds above Mach 6 and altitudes greater than 100 kilometers. The XLR-99 rocket engine used in most X-15 flights generated 57,000 pounds of thrust, more than 2 Eurofighter Typhoon engines in full afterburner. It ran on anhydrous ammonia and liquid oxygen. The rocket only fired for 80 to 120 seconds. After that, there was an 8 to 12-minute flight without power ending in a 200-mile-per-hour glide landing. The X-15 was a hypersonic research program, and lessons learned from it aided the development of the Mercury, Gemini, Apollo, and Space Shuttle programs. Number 2. X62 VISTA, Variable Stability In-Flight Simulator Test Aircraft. The versatile F-16 fighter has often found itself working in the realm of research. Over the years, F-16s have been fitted with an odd assortment of wings, control surfaces, inlets, nozzles, and black boxes. The X-62 is one of the latest in this long line of research F-16s. Starting as the NF-16D conversion of the F-16, it had a multi-axis thrust vectoring MATV engine nozzle that allowed a high degree of active control of the airplane in a post-stall situation. Put in simpler terms, the airplane's thrust could be steered to enable controlled flight in seemingly impossible directions or attitudes to the direction of flight. This could be used for a decisive edge in a dogfight, but has other interesting uses. The airplane could even be programmed to fly in similar ways to many other types, a great training tool. By obeying different control laws, it can be made to have the maneuvering characteristics of a variety of types, including yet unflown or enemy types. Later in its career, it was rechristened the X62 to fully acknowledge its contribution to cutting-edge research. It returned to explore the autonomous piloting of an airplane by artificial intelligence. In a historic moment, the X62, piloted by artificial intelligence, fought other U.S. fighters in a simulated dogfight and did extremely well. Number 1. Bell X-1 Second World War piston-engined airplanes could be dived at speeds approaching the speed of sound, around 760 miles per hour at sea level, but found some odd, unpredictable, and dangerous characteristics at such speeds. A media misunderstanding of this created a popular idea of a seemingly untraversable speed, the so-called sound barrier. The new technologies of jet and rocket propulsion made supersonic flight possible. Indeed, German B-2 rockets had flown at 3,580 miles per hour during the war. What was needed was a crewed airplane to prove that supersonic flight was safe for a person and to fully understand the aerodynamic peculiarities. A rocket engine was the simplest way to generate sufficient thrust, but its prodigious fuel burn meant such an airplane would need to be launched from a mothership at altitude to avoid the fuel-consuming process of taking off and climbing to height. The Bell X-1 employed a shape based on a .50 caliber bullet with a small straight wing. On 14th or in October 1947, test pilot Charles Chuck Yeager, pictured, flew the X-1, nicknamed Glamorous Glennis for his wife, launched from a B-29 mothership, and achieved a speed of Mach 1.06. The Bell X-1 was the first airplane to break the so-called sound barrier in controlled level flight. Thank you for joining us on this incredible journey through the top 10 extraordinary experimental aircraft. These remarkable machines showcase the ingenuity and daring spirit of their creators, pushing the boundaries of what's possible in aviation. If you enjoyed this video, don't forget to like, subscribe, and hit the bell icon for more exciting content. Until next time, keep dreaming big and flying high.